empirical probability means calculating probabilities by experiment. So you run out, you do an experiment, you collect your data, and you base your probabilities solely on that empirical data, solely on that experimental data. This is sort of the opposite of theoretical probability, which is what we're going to spend the rest of the chapter talking about, theoretical probability. So a theoretical probability is being able to just theoretically come up with numbers and predict what the probability would be. Empirical is solely based on experiment, and it probably has its roots sometime in the mid-1600s with a bunch of French mathematicians that were all gambling and playing gambling games. And they wanted to know, when should I bet? And how much should I bet? If I'm playing a hand of poker and there are cards on the table, what is the probability of me winning the hand? Or what's the probability of losing the hand? And I don't know if you've seen any of these, the television shows with the World Series of Poker, and they show the cards on the table and they got this little number off to the side that says, you know, the probability of winning the hand. Very interesting stuff, very interesting. So this is probably where it happened, of course, with betting and an exchange of money, okay? And so with this empirical probability, we came up with some vocabulary words. So some of these are pretty generic, and then others are very specific, like experiment, okay? That's the activity where you conduct an experiment and you find out results, okay? And those results are called outcomes. So you run an experiment and you end up with outcomes as a result of that experiment, okay? If you have a specific type of outcome, that can be called an event, and all of the events or the outcomes that satisfy a condition are called the event space. And this is an important vocabulary term that we're going to use a lot of, the event space, okay? All of the outcomes taken as a whole are called the sample space. So we have an event space, which are the outcomes that make up an event or a given condition, and the sample space. Now, when we get into calculating probabilities, this event space is going to be your numerator. That's going to be the number on top. And the sample space is going to become your denominator. Okay, so this is why they're important. Event space, the number of outcomes that satisfy a condition, and the sample space are all of the outcomes that are possible. And we'll get more into this when we talk about theoretical probability a little bit right now, though. So let's look at this example. Let's say that you have a six-sided die, and let's say that it's a fair dice, so each number is equally likely to come up. If you analyze it and say, what is the sample space? Well, the sample space are the six numbers, right? You could roll a 1, you could roll a 2, a 3, 4, 5, or 6. That's your sample space. But if you wanted to calculate the probability of rolling the number 6, this is a specific outcome. Okay, we're looking for the specific outcome of rolling a 6. That is your event space. And there is only one item in that event space. And so how would we calculate the probability of rolling a 6? And I know you're saying it's 1 out of 6, like you're screaming at the monitor right now. It's 1 out of 6, don't you know? That's theoretical probability, right? And we'll get to that. But for right now, we have to run an experiment. So you take a dice and you roll it, and your first number is the number 3. And then you roll it again and you get a 2. Or yeah, you roll it again. Your third roll is a 6. And that satisfies your event space, right? That satisfies the condition of rolling a 6. Then on your fourth roll, you get a 4. On your fifth roll, you get a 5. On your sixth roll, you get a 6. On your seventh roll, you get a 2. On your eighth roll, you also have an outcome that satisfies the given condition in the event space. Your ninth roll is a 1 and your 10th roll is a 4. So according to this, of the 10 rolls that you did, the number 6, the outcome that we're looking for, appears 2 times. So the probability is 2 out of 10. So you could kind of, in English language, you could say it's 2 out of 10, or you could say it this way. So 1 out of 5 is a fraction, 0.20 is a decimal, and 20% is a percent. And so we can represent this answer 3 different ways: as a fraction, as a decimal, or as a percent. And you need to make sure that you're fluid on being able to go back and forth between these 3 different ways, because sometimes the homework problem will ask you to write your answer as a decimal. Sometimes it'll want it as a percent. Sometimes you can write it as a fraction. Okay. So make sure that you can go back and forth between these 3 formats. Okay. So that's the probability. So what if we kept doing this? What if you're like, you look at this and you say, boy, that's a really small sample size. We only rolled the dice 10 times. What if we expanded our experiment? What if we rolled the dice 50 times, 50? So you roll the dice 50 times and you keep track of how many 6s you get, and you get 6 6s. And so your empirical probability, or the relative frequency, would be 6 out of 50, which is 12 out of 100, which is 0.12, which is 12%. So our probability went from 20% to 12%. And what if you say, well, we could probably do better. Let's roll it more. So you roll it 100 times, 500 times, 1,000 times. And each time you count the number of events that satisfy the condition. And you take those numbers and you make a fraction out of them. So you would take 163, you would divide it by 1,000. That gives you the 0.163, which is approximately 16.3%. And notice how our relative frequency, the number of times that it occurs, it seems to be approaching a value. We started at 20%, then we went to 12%, then 18%, then 16.2, and then 16.3. What would happen if we let n go to infinity? What if we could roll this imaginary dice infinitely many times? Well, if we did that, we would find that our relative frequency actually approaches the theoretical value. And so that's a good step into talking about theoretical. Now, here's the actual calculations that we've been doing, just sort of written out in fraction format so you can see it. So again, here are the conditions that meet our event space, right? That's the 163. We're taking row number 6, by the way, or not row number 6, but the row with the 1,000. So we're taking a look specifically at this experimental result right there, okay? So you take that experimental result and you roll the dice 1,000 times, 1,000 times. And of those 1,000 total events, 163 met the condition of being a 6. So you'd say the probability of rolling a 6, that's what this says. P means the probability of, and then what's in the parentheses is the event that you're looking for. The probability of rolling a 6 was 163 out of 1,000, which is about 16.3%. Okay. And the law of large numbers says that as n increases, the relative frequency tends towards the actual probability value, and actual meaning theoretical, the theoretical probability value. Okay. So that's a good segue right into theoretical probabilities. But before we get there, let's take a look at the 4.1 spreadsheet. Now, this spreadsheet doesn't actually have anything for you to calculate with. It's not a calculator. It's just more of a demonstration thing. So all you have to do is click on it, play with it a little bit, and then go ahead and submit. So nothing that you really need to calculate. But this Google Sheet has 2 simulators built into it. One is a coin flipping simulator where you're simulating the flip of a coin. The other one is a color simulator. So let's talk about the coin simulator first. So there are 10 trials. So you're flipping 10 coins, or you're flipping the same coin 10 times. We'll say it that way. And here are the results. And this is a formula. And to interpret this formula, I'll kind of walk you through it. There's a rand between function in here. So it says randomly pick a number between 1 and 2. So it's either going to pick a 1 or it's going to pick a 2. Okay. Randomly pick the number 1 or 2. The choose function then says, if you randomly pick the number 1, put the word or the letters HEAD in that cell. So put the word head in that cell. If you randomly pick a 2, put the word tail in the cell, okay? And so we do this for all 10 of these items. So all 10 of these have that same formula where it randomly picks a 1 or a 2. If it's a 1, it puts the word head in the cell. If it's a 2, it puts the word tail in the cell, okay? Then what we do is we count the number of heads and we count the number of tails. And we use the count if function to do this. So we say count if, and then we identify the range of cells, so B2 to B11, and then we put the word head in quotations to say, count the number of times the word head appears in these cells. Then we do the same thing for tails. Count the number of times the word tail appears in these cells. And so there are 3 heads and there are 7 tails for a total of 10 items, right? 10 outcomes. We then can calculate the probability of flipping a coin and getting a head by taking this value divided by this, and we can take the probability of getting a tail by taking the number of tails and dividing by the total number, okay? And so as you can see, this is randomly generated, but what this will do is it will randomly flip all 10 coins at the same time, keep track of the number of heads, keep track of the number of tails, and then calculate the probability in decimal format of getting a head and probability in decimal format of getting a tail. Sometimes students have this idea that when you're doing things randomly, you can't have streaks or like a bunch of tails in a row, that doesn't happen if something is truly random. And so this part of the spreadsheet shows the streakiness of 10 randomly flipped coins. So we start with, if it's a head, you start at the number 1. If it's a tail, you start at the number 0, okay? So in this particular case, we start at a tail, okay? So we start with the number 0. And then from there on, if you flip and get a head, you add 1. If you flip and get a tail, you subtract 1. And so this is a numerical way of sort of counting the heads and tails. So here we got a tail, so we subtract 1. Then we got a head, so we added 1. Another head, add 1. A tail, subtract 1. A tail, subtract 1. A tail, subtract 1. A head, add 1. What we can then do is graph this pattern, which is the line graph that you see right next to it. So as we refresh, look at that streak. Now, again, this is totally random. When you do this, you'll get a different pattern as I did. But look at this. We got 6 tails in a row. Tails, 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 tails. So start at 0, subtract 1, subtract 1, subtract 1, subtract 1, subtract 1. And then we get 4 heads in a row. 1, 2, 3, 4. And look at that graph. You can actually visually see the pattern of those 6 tails and then the 4 heads. Pretty interesting. Let's see if we get anything else that's interesting. This kind of looks like a mess. There's a 5 and 5, 50% for each one, a 6 and a 4, 7 and 3. Ooh, look at that. 9 tails. 9 tails. 7 of them consecutively. 9 tails in a row. I think I've gotten like all heads one time where they were like all heads. All 10 flips were heads. Rarely happens. But we're going to get into looking at like the probability of this happening. And so this is just something neat, interesting to play with. Oh, look at that one. Heads, heads, tail, heads, tail, heads, tail, heads, tail. Look, it's alternating, right? Again, totally random. So I could do this all day again. I just love the randomness of this. So very interesting to look at. Okay. We do the same thing. Down at the bottom, there's a tab. You can click on the color tab, and we do the same thing with colors. And so in this cell, you can see instead of randomly picking between 1 and 2, we pick 1 to 5. And so we say randomly pick a number between 1 and 5. If you pick a 1, write the word red. If you pick a 2, green, 3, blue, yellow, and orange, okay? So these are the things that we're randomly selecting as. And I have 19 of them. And I picked 19 because I wanted the denominator to be a messy fraction, right? Like 3 divided by 19 is a real messy fraction. And so here are 19 different colors. And then I did the same method of counting. So how many cells in the orange box are the word red? and how many are orange, and how many are yellow, and how many are green, how many are blue, add them all up, and then calculate the probabilities as a decimal. And then create a graph. And the colors of the wedges in the graph correspond to the colors that we're measuring. So you can just refresh these. And again, every time you refresh, all 19 colors are randomly regenerated. So let's see if we get anything interesting in this. Oh, look at that. Look at that. 9 reds. Holy cow. Red, 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 red. That's a lot of reds, right? No yellows. No yellows. So we randomly selected 5 colors 19 times, and there were no yellows and a lot of reds. Again, randomness doesn't mean evenly distributed. You can completely have a streak that runs, or a situation like this where you end up with one color that clearly dominates all the other colors. Randomness is like that. It's randomness is a little clumpy. This is empirical probability. We're doing an experiment, we're randomly selecting colors, or we're flipping a coin, and then we're just calculating probabilities based on the results of that experiment.